Okay, Bismillahirrahmanirrahim. Assalamualaikum. So today we're going to start a new topic, which is chapter number 4, chi-square test. So this is very simple topic. Hopefully we can finish it by today. So the objective for this topic is to understand two things. First is to understand the goodness of fit test, right? Goodness of fit test. Another one is to test for independence, right? Um, you can see my slide here. Nampak warna ni boleh nampak ah? Hello, boleh?
Boleh.
Alright. um, okay. So we start with the chi-square goodness of fit. So in this topic, we're going to learn two things. First is goodness of fit test, and another one is test of independence. So for the chi-square goodness of fit is a non-parametric test that used to find how observed value means the value that we found of a given polynomial is significantly different from the expected value. So the expected value is the value that we going to calculate, which is n multiplied with p. So in chi-square goodness of fit, the term of goodness of fit is used to compare the observed sample distribution with the expected probability distribution. We want to know the null hypothesis. There is no difference between observed and expected. The alternative hypothesis, we want to know, is there any difference between observed and the expected, right? So the chi-square goodness of fit also can be used to determine the theoretical distribution, such as binomial distribution, Poisson distribution, or normal distribution, or any other distribution such as uniform, um, and others, right? So when to use a chi-square goodness of fit? So this is appropriate when the following condition are met. First is when the sampling method is using a random sampling, right? It's not necessarily simple random, but it should be any random sampling, right? The variable under study is a categorical. So notice that in this topic we are discussing uh, on categorical data, right? But before this, in chapter number 1 until chapter number 3, we are discussing on numerical or quantitative data. So another one, if the expected value of the number of sample observation in each level is at least 5. So means that we in the data we're going to calculate the expected value. So the expected value should be more than or equal to 5. If you have expected value less than 5, means that we need to do some remedial action, right? So we cannot proceed with the Pearson chi-square. So now um, goodness of fit test. So this is actually a single categorical variable measured, and the exact numerical value are specified for each p. P means the probability or proportion for each level of the category, right? So if you still remember, goodness of fit test, we are measuring for a single categorical data. So let's say you still remember the frequency table. So let's say we have X and F, right? So and then we need to calculate another one is a relative frequency, right? Relative frequency. So P can be a relative frequency. So the frequency obtained from the performance of the experiment is called F observed frequency. So this frequency, right, is called as observed frequency. So the notation is as O, O1, O2, 03 and so on lah. So become because this is what we call as observed frequency. So then another term that you need to know in goodness of fit test is expected frequency. So the expected frequency came after the relative frequency, which is we need to calculate another column, which is expected frequency. Notation is E, right? So the expected frequency is, the formula for expected frequency is N multiplied with P, right? So N is the total number of sample size, right? Is the total number of sample size, and P is the probability that an element belongs to that category if the null hypothesis is true, right? So next thing that we need to know is the degree of freedom, right? The degree of freedom for a chi-squared goodness of fit test is k minus 1. So where k is the number of possible outcome. Let's say in frequency table, right? Let's say this is a frequency table. Let's say X, you have let's say Malay, Chinese, Indian, right? So the level or category that in this variable is k. So in this problem, we have k equal to 3. So the degree of freedom should be k minus 1. So 3 minus 1 should be equal to 2, right? So the test statistic that we're going to use is a chi-squared test, right? So the chi-squared test for categorical data. So chi-squared test for categorical data is summation of observed value minus expected value, then you squared, divide by expected value, right? So this is a formula for test statistics that we're going to use in our hypothesis testing. And remember, a chi-squared test is a right tail or one tail test to the right, skewed to the right distribution, right? So it's from 0 to infinity. So some notes that you need to know is some test statistics chi-squared only the test statistic chi-squared only approximate the chi-squared distribution, right? So that's why the approximation, if you want to the approximation to be accurate, then the expected value, expected frequency should be more than or equal to 5, right? For all cells. So the goodness of fit tests are different from the previous tests. Since the experimenter used null hypothesis for the model that he think is true. The hypothesis statement is whether the null hypothesis, the model is correct, and alternative hypothesis is the model is not correct, right? So now, to understand this further, how to apply the goodness of fit test. Now look at example. So example number 1. So in example number 1, let me put some space here. Right. In example number 1, a city expressway with 4 lanes in each direction was studied to see whether driver preferred to drive on the inside lane, right? A total of 1,000 automobiles, right, were observed during the heavy early morning traffic, and their respective lane recorded the result shown below. So this is we have actually 4 lane, right? This is the data recorded in the heavy early morning traffic. So for lane number 1, we observe 294. Lane number 2, 276 until lane number 4. So the question is, do the data present sufficient evidence to indicate that some lane are preferred over others? So means that they want to know whether is there any preferred lane in in the city expressway, or all lanes are equal, all preferred. So this one right, so this one, the hypothesis statement should be, so if you want to test whether all lanes are equal or at least one lane are preferred, so we need to find the probability value. The probability value here, since we have 4 lanes, right? So this one probability, right? Probability value, PI. So this one should be 1 over 4, 1 over 4, 1 over 4, 1 over 4, right? So the null hypothesis, P1 equal to P2 equal to P3 equal to P4, which is equal to 1 over 4, right? And alternative hypothesis, we want to test, is there any preferred lane over others? So at least one lane is not equal. Right, so this is our hypothesis testing, right? Okay. So let's assume that our alpha is equal to 0.05, right? So first, what we need to do is, the second step is to test statistic, right? To test statistics, here in goodness of fit test, we are required to find, let's say this is a chi-square test, right? Because we are calculating from a categorical data. So the formula for chi-square test is summation of observed minus expected squared divided by expected value. So we need to find the value of observed, which is we already know, and we need to find the value of expected frequency. So let me create a table. So 6, 5. Right. Let's say this is lanes, and this is observe, and this is expected. Let's say this is O minus E, and this is O minus E squared, and this is O minus E squared divided by E. So let's say this is lane number 1. Sorry. This is lane number 1, 2, 3. 3, 4. Right. This is total. So this is 294, 276, 238. This is 192. Right. The total should be equal to how much? Right. The total should be equal to 1000, right? So 294 plus 276, 238 plus 192, 1000. So the expected frequency here, right? So the formula of expected frequency is N multiplied with P, right? So N is equal to 1000 equal to N, right? And P is equal to 1 over 4. So this is the probability that we want to find. So N 1000 multiplied with 1 over 4 is 250. So all is going to be same because the probability are same for every lane, right? So observed minus expected. So 294 minus 250 equal to 44, right? 250. This is 276 minus 250. This is 238 minus 250. And last is 192 minus 250, right? 58. And then next is 44 power of 2, right? So you need to calculate for every cell. So this one should be 676. This is 144. And this is 3,340, 64. And this one you need to divide by 1936 divide by the expected frequency 250 should be 7.744. So this one should be 2.704. This is 0.576. This is 13.456. And the total for this column is 24.48, right? So we know that the chi-squared is equal to summation of observed minus expected square divided by expected should be equal to 24.48. So this is the chi-squared calculated, right? Are you okay? So next, the next step is we need to do a critical region. So critical region. But before we proceed with critical region, we need to check for each expected value. So we need to make sure each expected value is more than or equal to 5. So since every row for expected frequency is more than 5, so we don't need to worry. We can proceed with the critical region. So our critical region is by using a chi-square distribution, right? It's a skew to the right distribution. So we want to find the probability of 5% error. So this is a 0.05. This is a rejection area. So the chi-squared is df and 0.05. So the degree of freedom is k minus 1. So how many k we have? We have 1, 2, 3, 4. We have 4 lanes, right? So we have 4 category. 4 minus 1 should be equal to 3. So the chi-square that we want to find is degree of freedom equal to 3, 0.05. So this one should be equal to 7.81473, right? So this is 7.81473. So the next step is we need to do a decision. So our decision is if chi-squared calculated more than 7.81473, then null hypothesis is rejected, right? So um, since our chi-squared calculated is more than 7.81473, then we reject null hypothesis. Right, then our conclusion is at least one lane is not equal, right? Or we can say that the data presents sufficient evidence to indicate that some lanes are preferred over others, right? So that is our conclusion lah. So are you okay? Right. Um, so let's move to the next example. We try to finish by today. The example number 2, same process, right? So now this is quite different between compared to example number 1, right? The proportion of blood type O, A, B, and AB in XYZ this population of a particular country are known to be ratio 50, 30, 15, 5 respectively. So a research team investigate a small isolated community in the country and obtain the following frequencies of blood pressure. So we have, this is a blood type, and this is a frequency that the observed frequency for isolated community. So test at 0.05 level of significance whether the proportion in this community differs significantly from XYZ population. So now, so the hypothesis statement will be a bit different because we have the proportion here, right? So if blood O means 150 over 100. So this one should be equal to 0.5 or 1 over 2, right? And this one, this is, yep. So the second proportion is 30 for B, right? For A, sorry, for A. 30 over 100. So this one should be equal to 1 over or 3 over 10. Right. Another one is 15 over 100 should be equal to 3 over 20. And the last one is 5 over 100 should be equal to 5 over 100. So now the null hypothesis, right? It should be the proportion ataupun or we can put as P1 equal to P2 equal to P3 equal to P4, and then alternative hypothesis at least one is not equal, or we can say that the alternative hypothesis, the proportion, right, do not differ, and alternative hypothesis, the proportion is differ. So I choose the first one. The best is the first one. So we know that from here, our P1 is equal to 1 over 2. P2 is equal to 3 over 10. P3 is equal to 3 over 20. And P4 should be equal to 5 over 100. So alpha is 0.05. So this is our alpha. The next step is we want to find the test statistic. Right, our test statistic, we need to find expected value and expected frequency and observed frequency. So this is going to be blood type. This is observed frequency, and this is going to be our P, because our P now is not equal, it's not same for every blood type, right? And then we need to find the expected frequency, and then the O minus expected frequency power of 2 divided by expected frequency, right? So this is what we want to find lah. So let's put in a nice table, right? So this is O, A, B, and AB, right? So the frequency here is 90. This is 50, 20, and last is 10. So probability or proportion for O, blood O, is 1 over 2, 2 over, 3 over 10, and second last is 3 over 20, last is 5 over 100. So the total for observed frequency is 170. This is total. And the total here should be equal to 1, right? So the expected frequency is N multiplied with P, right? Is equal to expected frequency. So this one, 170 multiplied with 1 over 2 is equal to 85. So same as second row. This is going to be 51, 25.5, and this is 8.5, right? Then the observed minus expected, maksudnya because this one means 90 minus 85 power of 2 divided by 85. So this one should be equal to 0.2941, and this is 0.0196. This is 1.1863, and the last one is 0.2647, and the total is the total for chi-squared value. Actually, this is a chi-squared, right? This is a chi-squared 1.7647, right? So from here, we know that our chi-squared calculated is equal to 1.7647, right? So we proceed with the next step, which is our critical value, right? Our critical value is critical value or critical region, right? So we're going to use a chi-square distribution, skewed to the right distribution, right? This is our rejection area, which is 0.05. So this is a chi-squared with degree of freedom and alpha. So chi-squared, our degree of freedom here first, our degree of freedom is k minus 1. So our k is equal to 4 minus 1. Right. So now, it should be equal to 3. Right. So degree of freedom is 0.05. This is our alpha with degree of freedom 3. So this one should be equal to 7.813. Right. This is 7.813. Next is our decision. Right. So decision, since chi-squared calculated is less than 7.813, then null hypothesis is accepted. And the conclusion is, so we conclude that the proportion is not differ significantly from XYZ population. So that's how we do it to test to test goodness of fit test, right? So I have another example, but this one I'm going to leave it to you. Please do it by yourself, because this one you need to find. This one they already give you the P, right? This is your proportion, right? 24, 41, 24, 26, and 29 and 9%. So this one I require you to solve it and put it into a flip grid, right? So now we're going to look at another application of goodness of fit test. So which is we can find uh, we can test whether the distribution or data is follow the certain distribution or not, right? But we're going to focus on binomial and Poisson, even though we can do it in with normal distribution or other distribution. Right, the steps are same. That now I'm let look like at this one first, right? So others application of in goodness of fit test, right? So it is possible to design a goodness of fit test to determine whether the data are consistent with data drawn from particular probability distribution, such as a binomial distribution, Poisson distribution, normal, uniform, and others, right? So, but you need to understand the step. So once you understand the step, then everything going to be very easy. Right. So step number one to test goodness of fit for particular probability distribution. So first is the data is follow type of distribution, whether Poisson, binomial, or normal, right? And alternative hypothesis does data does not follow Poisson, binomial, normal, or uniform. And then step number two, you need to find the probability value using the formula of particular probability distribution. If you are testing for Poisson distribution, you need to find the probability value based on Poisson for PDF. If you are using binomial distribution, you are testing binomial distribution using binomial PDF. If you are normal, using normal PDF, right? Right, and then step number three, you need to find the expected value. Same as previous uh, step, you need to find the observe, you need to find the probability and expected value. So the expected value is, this is expected frequency actually. E is equal to N multiplied with P. If E expected frequency is more than 5, right, then it should be okay, right? We can proceed with no uh, as usual, right? If expected value is less than 5, which it should be less than 20% for on the cell of the cell, right? If more than 20%, then we cannot proceed with Pearson chi-squared statistics. So step number 4 is by using our test statistic, which is uh, chi-squared Pearson chi-squared statistic. So same formula. The critical region, the critical value, we need to find the critical value on the right tail, because the chi-square is a right tail distribution. The degree of freedom is k minus 1, where k is the frequency and or category, and the number of restriction must be total must agree is 1. So we need to minus 1. This is a normal step as we done it before. So now look at example number 1 for others application in goodness of fit test. So now so example number 1, there are 1,000 bags of orange, each bag contain 10 orange, right? Some of the orange are rotten, and is the distribution of rotten orange in the individual bag having a binomial distribution? So we want to know whether uh, the distribution of rotten orange is follow binomial distribution. So from here we know that our n is equal to 10, right? This is our n, and we don't know the value of p. So x is having a binomial distribution with n equal to 10, and p is, we don't know the value of p. So now the null hypothesis should be the data follow binomial distribution. The roten, so we should put this way: the count of roten orange follow a binomial distribution. So this is our hypothesis. The alternative hypothesis means the other way lah. The count of rotten orange does not follow binomial distribution, right? So our alpha, let's put as 0.05, right? So then we need to find test statistic, right? So our test statistics, since we are dealing with categorical data, right? We're going to use a chi-squared this test. So now we know that X is having a binomial distribution with n equal to 10, and we don't know the value of P. So to estimate P, right? The estimate P, it should be X bar divided by n, right? So n is the total number of trial, right? X bar is since this is a categorical data, X bar is summation of fx divided by summation of f and divided by n, this n. So it should become summation of fx divided by summation of f multiplied with n. So this one should be, you need to calculate by yourself. F is 334 multiplied with 0, right? 369 multiplied with 1, and the total should be equal to, divide by this one, should be equal to 0.1142, right? So then we need to calculate the value, we need to put into a table, very nice table, right? So we can calculate the value of chi-squared. So this is basically number of rotten orange, right? Rotten orange, and we have observed value, right? And we need to find the probability value and expected frequency, and the last one is a chi-squared value, which is some observed minus expected squared divided by expected. So this is 0, 1, 2, 3, 4, 5, 6, right? We do have until 6, right? So this one put into a nice table. Right. The value of observe is 334, 369, 191, 63, and this is 22, this is 12, 9, right? So the value of probability, right, we need to apply the probability distribution function for binomial distribution, because we are testing binomial distribution. So n choose x, p power of x, right? And 1 minus p power of n minus x, right? So this one should be 0. So n is equal to 10. 10 choose 0. P is equal to 0.1142 for the first row, right? Power of 0, right? And the complement is 1 minus 0.1142 n 10 minus 0, right? So this one should be equal to 0.29 0.2974. So this is 0.2974, right? So the next one is 0.3834, 0.2224. This is 0.0765. This is 0.0173. This is 0.0027. And the last one is 0.0003. Right. So now we know the value of summation total observed is 1000. Right. So the expected frequency is n multiplied with p. So n is 1000 multiplied with p is this value 297.4. This is 383.4. 222.4. This is 76.5, 17.3, 2.7, and the last is 0.3. Right. So now, if you look at the expected value, right? If you look at the expected value, right? We agree that before this, if you want to proceed with Pearson chi-squared, right? The expected frequency should be more than 5, right? So now, if you look at this one, there are two cell less than 5. Less than 5. So what we need to do is, let's say I clear this one first. I don't want to create another table, right? So I clear this one. Right. Let me clear this one dulu. Right. Let me copy this one and put a bit further from my, right. So let me create another new expected value. So I need to combine these two together. If I combine these two together, it's still 2 point, or it's still equal to 3, right? Right. So if, remember this one, right? Let me go upstairs a bit. Wait, yeah, this one. So if expected frequency less than 5, it should less than 20% of the cell, right? It means that now we have 1, 2, 3, 4, 5, 6, 7 cell, right? So now 2 out of 7 is less than 5. It become 28%, 28.57%, right? 28.57%, which is more than 20%, right? So now what we need to do is we're going to combine these two, right? If we want to reduce until 1 over 7, it should be only 1 over 6. 1 over 6, it should be 16.67. So if we combine these two cell, right, to become 1, because so it become 3, right? And then we only have 297.4, 383.4, 222.4, 76.5, 17.3. So now we have only 1, 2, 3, 4, 5, 6 cell. So only one cell here is less than 5. So 1 over 6 multiplied with 100%, we only have 16%. So it's not more than 20%. So we can stop, we can combine only these two only. We don't need to combine 3 cell, right? So then the next step is we need to find the value of chi-squared. So the value of chi-squared here is, it should be chi-squared summation. So no need to do summation because we need to calculate for individual cell. So this is O minus E squared divided by E. So this one should be 334 minus 297.4 power of 2 divided by 297. So this one should be equal to 4.5042. This is 0.54085. This is 9.8. Sorry, 9.4. 9.4318. This is 2.3824, and this is 1.2769, and the last one is 108. Is it? Let me calculate first. So 108 means this is 21 minus 3. 21 minus 3 power of 2 divide by 3. So 108. Yep, correct. So the total here should be equal to 121.13. So this is the value of a chi-square. Right. So now our chi-square calculated is equal to 121.13. So the next step is we need to find we need to create our critical region, which is skewed to the right distribution. This is rejection region, which is 0.05 equal to our alpha. So this is chi-squared, degree of freedom, and alpha. Right. So now our degree of freedom here is quite different compared to a previous example. The degree of freedom is k minus 1, right? K minus 1 is total that we agree, and we need to minus another one because we are computing the probability value here. We are computing using the data, right? So since we are using data to compute the probability value, right? So we need to minus another one, right? So this one should be equal to, so how many class we have? We only have 1, 2, 3, 4, 5, 6. 6 category. Compared to the first one, we have 7. 1, 2, 3, 4, 5, 6, 7. But we already combined these two cell to become one. So we only have 6 cell. So 6 minus 1 minus 1. So it should be equal to 4. Right? So our chi-squared for 0.05 is equal to 13.277. Right? So next what we need to do is to make our decision and conclusion. So our decision is, since chi-squared calculated is equal to 121 is more than 13.277, so the null hypothesis is rejected. Right, our conclusion is the data does not follow binomial distribution. Right, so that's how we do it lah. Are you okay? Do you have any Any questions so far? Right. So let's look at another example. Right. I have example until example 5, but I'm not going to go through every example. I just showed you example for binomial distribution. So let's look at example for Poisson distribution. Right. Example for Poisson distribution. Let this. Yep, example number 5. So later I will give you this note. I'm going to leave example number 2, example number 3, example number 4 for you to do it by yourself and submit as assignment, right? Because this is very simple, same procedure as example number 1, right? So no need to repeat the same thing, right? Now look at example number 5. So example number 5, so this is the number of computer malfunction per day is recorded for 260 days, right? With the following result. So we have a computer a number of malfunction 0, 1, 2, 3, 4, 5, and a number of days 77 until the total should be equal to 260, right? So now test the goodness of fit of the appropriate model. So this is actually a Poisson distribution because we are dealing with the um, count data. So this is number of malfunction. This is number of days, right? So this is a count data. So because one of the thing is the malfunction occur independently, right? So another one is the malfunction occur randomly in time, right? Number of days, right? So this is what or why because why we say that this is a Poisson distribution, right? So we can prove it if so to say that this is a Poisson distribution, we can prove it if the mean, the expected value of x should be equal to the variance of x. So you remember, the mean and the variance for Poisson distribution is same, right? So now we need to prove it first. Expected value of x is equal to summation of fx divided by summation of f. So this one should be equal to 0 multiply with 77 plus until 3 multiply with 5, right? Divide by the total number of frequency is 260. So this one should be equal to 1.25. And the variance of x is equal to summation of fx square minus summation of fx, and you squared here divided by summation of f divided by summation of f minus 1. So this one should be equal to 735 divided by 260 minus 1.25 squared. So this one should be equal to 1.26. So if you notice, the variance and expected value is a close value, very close value to 1.25 and 1.26. So then we can conclude that our lambda is 1.25 or 1.26. I more prefer is to 1.25. Right. So next, we can proceed with our hypothesis testing. So hypothesis testing. So the null hypothesis is number of daily malfunction is follow Poisson distribution, right? The alternative hypothesis, number of daily malfunction does not follow Poisson distribution, right? So let's set our alpha 0.05, right? So the next step is same step as before. This is test statistic. So that's why if you want to test for other type of distribution, it's the same process, right? So this is your x, right? Let's say the x is a number of malfunction, right? And we need to find the observed value, right? Which is your frequency. This is 0, 1, 2, 3, 4, 5, right? We only have 5, right? 5 malfunction. So this is, we need to put into a nice table, right? So the observed value is, this is 77, right? 77, 90, 55, 30, 5, and 3. The total is 260. This is total. And next is we need to find the value of probability, right? The value of probability. And next is expected frequency. And last is observed minus expected squared. This is observed minus expected squared divided by expected. So the value of probability here, right? The value of probability here is by using a Poisson distribution, right? Expected negative lambda divided by x factorial. So for the first row, when px equal to 0, so lambda is 1.25 power of 0 exponential negative 1.25 divided by 0 factorial. So this one should be equal to 0.2865, right? So this is 0.2865. This is 0.3581, 0.2238, 0.0938. This is 0.0291, and the last one is 0.0073. And the expected frequency is n multiplied with p, which is 260 multiplied with 0.2865. So this one should be equal to 74.5, 93.1, 58.2. This is 24.2. This is 7.6. Sorry. But before you start with this one, I think something not correct. We need to make sure the total probability here is equal to 1. So the total probability here, if you total the value of probability here, is not equal to 1, right? So if you want to make it equal to 1, then 1 minus summation of probability of x, right? So this one should be equal to 0.0019. So this one should be nothing here. There are no value here, right? Right. This is no value. And the total should be 260. This is total. And the cell here should be more than 6, right? More than or equal to 6, right? So now this one should be 1 point 9. This is last is n multiplied with p. N is 260 multiplied with p is 0.5. So now we, instead of having 6 cell, now we are having 7 cell. Because the probability value, the sum of that on the total of the probability should be equal to 1, right? So now, since we have a 7 cell, so now we look at the, we could look at this one, right? We can, since this is no value here, right? We can, basically we can ignore this one, but we cannot ignore like that. So look at this one, 1.9 and 0.5. So 1.9 plus 0.5 is still less than 5, right? If you want to combine this one, right? So let's say we combine these 3 cells together, because if you look at this one, there are no value here. So the best is we combine this cell together, become 3 cell into 1, right? So this one should be equal to it should be equal to how much? 7.6 plus 1.9 plus 0.5. It should be equal to 10, right? It should be equal to 10. So our new is 10. New expected value is equal to 10. So others 2 is not usable. So this one is 0.084. This is 0.103. This is 0.176. This is 1.39. This is 0.4. The total here should be equal to 2.153. Right. Right. So now our chi-squared calculated is equal to 2.153. Right. So next we need to find the critical region. So our critical region is on the left right hand side, right? Still same. So this is a rejection region, and this is a chi-squared, degree of freedom, and alpha. So our degree of freedom here is k minus 1. We need to minus another 1 because we are using the data to calculate the probability. So how many k we have? We have basically 1, 2, 3, 4, 5, right? So this is number 1, 2, 3, 4, 5. We only have 5 category. So k is equal to 5 minus 1 should be equal to 3. So our degree of freedom is equal to 3. And when degree of freedom is equal to 3, chi-squared, 3 degree of freedom, alpha 0.05, so should be equal to 7.815, right? So decision, if chi-squared calculated, right, is more than, so we make our decision, right? Wait. Since chi-squared calculated is less than 7.815, null hypothesis is accepted. So our conclusion is the number of computer malfunction per day does follow Poisson distribution, right? So that's how we do it. Right. Do you have any questions so far? Right. So if you don't have any question, then we can move to the next topic, which is our last topic for chapter number 4. Our last topic in chapter number 4 is test of independence. So different with test of goodness of fit, right? In goodness of fit test, we are testing the hypothesis for a single categorical variable, right? For test of independence, we are testing the hypothesis for two categorical variable, right? We need it involve two qualitative variable, which is two categorical variable, and the data using the display in contingency table. So contingency table, this is a contingency table. We have row and column, right? We have row and column, right? So R multiply R by C contingency table, right? So so the chi-squared of chi-squared test of independent, the hypothesis is classification are independent. Classification means the categorical data. The two categorical data are independent. The alternative hypothesis, classification are dependent. So observed cell count for row uh, is denoted as O, right, which is your frequency value. The expected cell count are N multiplied with P, right? If null hypothesis is true, then the classification are independent. The P is the falling P, a probability of falling in row I multiplied with probability is falling in row J. So before this, we are having a single categorical data. So if you want to calculate calculate expected frequency for goodness of fit test, so the expected frequency is N multiplied with P. But for test of independence, we have two categorical data, right? So if you want to calculate expected frequency, then it should be equal to number of row. So mean row total, not number of row total multiply with column total divided by grand total, which is a sample size, right? So we are still using same test statistics, right? Which is chi-squared test, summation of observed minus expected square divided by expected. But now the degree of freedom for this test statistics a bit different. R minus 1 means number of row minus 1 multiply with number of column minus 1. So this is our degree of freedom, right? So the step of conducting hypothesis testing for independent independent test, chi-square independent test, is first we need to state the hypothesis statement. Classification independent, and the alternative hypothesis is classification is dependent, right? And then we need to find the expected value for each cell, right, which is rows so total multiply with column total divided by grand total. And then we need to find the value of chi-squared calculated, right? And then if you have 2 by 2 table, you need to calculate the chi-square using a Yates correction. Yates correction means observed minus expected, taking a absolute value minus 0.5 and squared divided by 2. So this is the formula for Yates correction. So Yates correction is only applicable when you have 2 by 2 table. If you have more than 2 by 2 table, you should use the normal Pearson chi-square test. So the critical region by using the degree of freedom R minus 1 multiply with C minus 1, and decision and conclusion are same. Now look at example number 1 so we can understand what I said before. So example number 1, in example number 1, violence and lack of discipline have become major problem in school in United States. A random sample of 300 adults was selected, and they were asked if they favor giving more freedom to school teachers to punish the student for violence and lack of discipline. So two-way classification table as follows. So we have in favor is and against and no option, and we have another one is man and woman, which is this is a gender, right? So now the question asks us to calculate the expected frequency for this table. So now we need to create a table, a proper table, because in a proper table with expected frequency we should have a total, right? So this is, we have 3 column, right? With another one is total, and another one is we have man, woman, and total. So this is man, woman, total. This is in favor. This is against. This is no opinion. This is total. So the value of observe is, let me put in blue color. This is observe 93, 87, 70, 32, 12, 6, right? And the total is, for men is 175, for women is 125, and in favor should be 180. This is 102. This is 18. The grand total is equal to 300. So now, if we want to find the expected frequency is equal to row total multiply with column total divide by grand total. So if you want to find for men in favor, row total is 175 multiply with column total is 180 divide by 300. So this one, the expected frequency is 175 multiply with 180 divided by 300. So this one should be equal to, this one should be equal to 105.0, right? And this one you need to calculate for everything. This is 175 multiply with 102 divided by 300. So this is 59.5. 175 multiply with 118 divided by 300 is 10.50. This is 125 multiply with 180 divided by 300 should be 75. This is 125 multiply with 102 divided by 300, 42.50. And the last one is 7.5. So this is expected frequency, and we need to look at the value of expected frequency. If there is there any expected frequency less than 5, so there are no expected frequency less than 5. So we can proceed with the Pearson chi-square test, right? So if we have expected frequency less than 5, we need to make sure that the expected frequency less than 5 is not more than 20%, right? Before you proceed. So now, look at example number 2. In example number 2, right? Example number 2, it referred to example number 1 just now, right? So a random sample of 300 adult was selected, right? So based on the result survey, a two-way classification table will present, right? We already looked at this one. So does the sample provide sufficient information to conclude that two attribute, gender and opinion of adult are dependent? Use 1%. So we need to test the null hypothesis. We need to state the null hypothesis. The null hypothesis is gender and opinion of adult are independent. So they are not related, right? So alternative hypothesis, gender and opinion of adult are dependent. So they have a relationship. So alpha is 0.01. So our test statistic, right? So our test statistic is chi-squared summation of observed minus expected squared divided by expected. So this one should be equal to observed minus expected 9 minus 105. So this is not 9, this is 93, right? This is 93. So 93 minus 105 power of 2 divided by let me put this way, 93 minus 105 power of 2 divided by 105 plus 70 minus 59.5 divided by 59.5 plus until 6 minus 7.5 power of 2, right? Power of 2 divided by 7.5. So this is the chi-squared distribution, chi-squared value, right? So this one should be equal to basically this is going to be 8.252, right? So the next step is we need to find the critical region, right? Our critical region is still using a skewed to the right distribution, which is chi-square distribution. So this is 0.01 chi-squared degree of freedom 0.01. So our degree of freedom here is row minus 1 multiplied with column minus 1. So number of row here is we have 2 rows and number of column we have 3 column. So 2 minus 1 multiply with 3 minus 1. So this one should be equal to 2, right? Right. So the chi-squared with 2 degree of freedom and 0.01 is equal to 9.21, right? So our decision, since chi-squared calculated is less than 9.21, null hypothesis is accepted, right? So conclusion is, our conclusion is, since we fail to reject null hypothesis, we can say that gender and opinion is independent. So they are not related to each other, right? So now, are you okay with this one? Are you okay? We're going to look at a last example and we conclude our chapter number 4. Right. Right. Now look at last example number 3. Right. So if you still remember this one, I put in this one. So if we have 2 by 2 table, we need to use eight correction. If you have more than 2 by 2 table, we use a normal Pearson chi-square. Right. So now look at example number 3. We have a 2 by 2 table. A researcher want to study a relationship between gender and owning cell phone. So she took 200 adult, right, as a sample and obtained the information as in table. So they have man and woman, right? And then they have own cell phone and no cell phone. So now at 5% level of significance, can you conclude the gender owning cell phone are related to adult? So this is test of independence. So now, first step, what we need to do is to state the hypothesis statement. So the hypothesis statement, null hypothesis is gender and owning cell phone are independent or not related. You can put that one. Alternative hypothesis, gender and owning cell phone are related, right? Either you can put not related or independent or related or dependent. It doesn't matter. So our alpha is 0.05. Now we need to test statistic. So our test statistic, we need to find the expected frequency, right? So we need to create another table, right? So we have this is man and this is woman, right? And this is total. This is own, not own. This is total. So the value of own and man is 640. This is 450. And this is the 1090. This is 440. This is 470. This is 910. So this is 1080, 920, and the grand total is 2000. So the expected frequency, this is actually observed, right? The expected frequency is 1090 multiplied with 1080 divided by 2000. So this one should be equal to 588.60. This is 501.40. This is 491.40. This is 418.60. Right? So this is the expected frequency. Now, we need to calculate the chi-squared value. So the chi-squared value for 2 by 2 table is observed minus expected, right? The absolute value observed minus expected and minus 0.5 divided by E, right? And don't forget, you need to square this value. So this one should be equal to 640 minus 588.6, taking the absolute minus 0.5 and square. Divide by 588.6. So this one plus 450 minus 501.40, right? Taking the absolute minus 0.5, right? This is square divided by 501.4 plus the third one is 440 minus 491.4 taking the absolute minus 0.5 squared divided by 491.8 0.4 sorry, plus the last one is 470 minus 418.60, right, minus 0.5 squared divided by 418.60. So this one should be equal to 21.03, right? So we already know the value of chi-squared. So now next is our critical region, right? So our critical region, our chi-squared is degree of freedom and alpha. Alpha is 0.05, right? So before that, we need to find the value of degree of freedom, right? So our degree of freedom is R minus 1 multiplied with column minus 1. So this is column, a row we have 2 minus 1, column we have 2 minus 1 should be equal to 1. So degree chi-squared with 1 degree of freedom, 0.05 is equal to um how much? 3.841, right? So the area that we want to find is on the right hand side. So this is the rejection area. So 0.05. So our decision is since chi-squared calculated is more than 3.841, which H null is rejected. So our conclusion is, we can conclude that gender and owning a cell phone are related. So by then, I think it conclude chapter number 4 and conclude our syllabus in QMT 261. And remember, you have assignment to do, right? Example number, the example that I leave it to you just now, right? Example number 2, 3, 4, just three questions that you need to do as your assignment, right? For your understanding. So do you have any questions so far? Any questions so far? Do you have any question? So if you don't have any question, then I think we already complete our syllabus content, and I think that's all.